Welcome to week 4 of the course on global civics. This will be talking about climate change. There is no other force that has rendered the national borders as porous as climate change. That is because the emissions that you personally cause and emissions from halfway around the world make no difference. They all go into the same atmosphere and they have the same consequences for you personally. Furthermore, even the most powerful country cannot stop the effects of climate change on its borders and somehow insulate itself from climate change. So as such, climate change is the paradigm case for our increasing global interdependence. Our lecturer this week is Professor Hans-Joachim Schnellnhuber. He is the director of the Potsdam Institute. He is not only the leading German scientist on climate with cutting-edge data and analysis, but he is also one of those rare people who ventures on to thinking about possible solutions to climate change by using big, enduring ideas from Kant. His lecture is full of data, graphs, different units. Do not be disheartened if you are confused at times. You have the option to stop his lecture at any time. You will also have access to his PowerPoint presentation as a separate file, which you can study at your own pace. Here's Professor Schnellnhuber.
Hello, everybody. I'm John Schnellnhuber. I'm a climate scientist working at the Potsdam Institute for Climate Impact Research, and I'm very happy to participate in the Global Civics project. I will talk today about an issue I have been working on for some 30 years now. It's about global warming or man-caused climate change, and the overarching questions I'm trying to answer is why climate protection and why and how. So I'll try to talk you through a few slides that actually will reflect the state of the art of the science. But then I will touch upon also how we might actually solve the problem, how we might solve it in the spirit of the Enlightenment, and actually also in the spirit of the philosophy that accompanied and brought to maturation the Enlightenment, which I would call the Kantian approach. Okay, so here we go. First of all, I'd like to draw your attention to the fact that the climate we are operating in today is not at all the norm, actually. It's the exception in the history of our planet. So what you see here now is more or less a chart back in time about 100,000 years of global mean temperature. So we have fantastic archives now, in particular ice cores, which we can use to reconstruct the previous climate. We actually can go back about 1 million years and year by year sort of reconstruct the climate at those times. What you see here now is that during the last 100,000 years, which mainly means during the last ice age, we had wild fluctuations of mean temperatures. And I can actually try to make a movie out of that. So you see planet Earth, so popping up and down, oscillating wildly along the time axis until finally, over the last about, 11,000 years, so you see here the red circle, we have an extremely stable climate. So this is a complete exception. Now, if you go back in time, Homo sapiens, human beings have been around for, we can argue, maybe 150,000 years. Now, at certain points in time, for example, here, you see about 70,000 years ago, through genetic analysis, we can estimate that during that time, only 15,000 individuals of the species Homo sapiens survived. If you compare it to the expectation that in the year 2050 we will probably have 9 billion of our kind on this planet, so you see humanity was very close to extinction during these wild fluctuations of the global climate. But now we are living in what experts call the Holocene, that is an extremely stable climate. You still have fluctuations, of course, but it's nothing compared to the wild roller coaster behavior of the climate during the last ice age, for example. And this actually was the basis for what we call the Neolithic Revolution. Again, you see here the fluctuations, and then at a fairly warm level, because we are now between the ice ages, the climate settled in a fairly stable state. And this allowed humanity to become a settling civilization, a culture in the true sense of the word. That means developing agriculture on the site where people stayed and lived. This brought about what we now call the Neolithic Revolution, which was, if you like, the Big Bang of civilization. So that happened around 8,000–9,000 years ago and developed into our civilization here. And you can see this is where we have ended so far. That means we have megacities all around the planet. But it all comes from this benign stability of the climate, which happened and started 11,000 years ago. Now, this is not going to last. If we zoom in now into the last 10,000 years here, so we look in more detail into what we call the Holocene. You see now this is a fairly recent reconstruction. Actually, the paper appeared just 4 weeks ago of the climate state. And you see now that in the early Holocene, so around 8,000, 6,000 years ago, it was actually warmer than throughout most of the period. And then slightly and slowly the climate cooled again until finally you see a spike. And also if you look into more detail the last 2,000 years, you see this spike that started around 1950 actually. And this is the interference of human civilization with the natural climate system. This is driven by greenhouse gases emitted, in particular CO2 from industry, from domestic use, from cars, and so on. And you clearly see that the natural pattern is broken by this human interference. So, that means we are about to bring the Holocene, this benign period of stability, to a crushing and crashing end. And that is the challenge we have for the climate. Now, as I said, it comes about from more or less the Industrial Revolution, which was based on the Paleolithic and Neolithic revolutions. So what you see here is the global energy mix, charted here from 1850. So you see human civilization always used biomass, collected wood, things like that, burned it. But around 1750, slowly and later on, coal became the fuel which propelled the Industrial Revolution. Later on, around 1950, oil became really dominant. It was cheap oil, in particular from the Middle East. Gas completed the picture. And then a little bit of nuclear, you see, and a tiny fraction, a tiny added layer of renewable energies. So that is the energy mix, if you like, of modern civilization. And this, of course, means that we burn a lot of carbon and fossil fuels, and the emissions will actually destabilize the global climate system. Now, when People have talked a lot about whether this will really change the climate according to the predictions of the science. In particular, people have argued during the last 10 or 15 years, global warming has slowed down or even stopped. Now, if you take a closer look of the data, you see that this is not true. So, for example, we looked between 1980 and 2010. That is a paper done by Foster and Warmstorff, so colleagues of mine here at the Potsdam Institute. If you look at the raw data between 1980 and 2010, global mean temperature, or actually the deviation from the mean, the long-term mean. And these are different data sets provided by different centers in the world, United States, Japan, UK. What really matters is the development of that, not the absolute height, so to speak. Now, if you normalize this, so you have a common starting point, more or less, and you take out natural variability. Natural variability means volcano eruptions, which cool down the climate, at least for 1 year or two. Oscillations or changes in insolation, that means the sun may become slightly weaker. In general, this happens in an 11-year cycle and stronger again, but these are tiny, tiny modulations of the overall insolation. And even more important and very important, I come to that also in the next slide, that is the so-called El Niño phenomenon. Now, El Niño means the child, and it was first noticed by a Peruvian fisherman that around Christmas, actually, the sea off the coast tended to warm up considerably, which was very bad for the fish catch. And El Niño is a sort of irregular warming of the eastern Pacific Ocean. And it means that during El Niño years, the ocean delivers heat to the atmosphere. There's a net loss of the ocean heat to the atmosphere. This is followed up in general by La Niña, the girl, in Spanish, which is the cold counterpart, so to speak. It's a wave or anti-wave coming after El Niño. And during that period, the ocean actually sucks up heat from the atmosphere. So we see it as a cool phase in sea surface and actually atmospheric temperature. Now, if you remove all these natural variabilities, so we really look at a specific year, was it an El Niño year, warmer than usual, a La Niña year, cooler than usual? When you see these data all converge and collapse onto something like an almost linear increase, even during the last 2 decades of global mean temperature. So clearly you have the climate trend, and this is clearly due to human interference. And this is actually following more or less precisely the laws worked out almost, or actually more than 100 years by Svante Arrhenius, a famous Nobel laureate in chemistry, who for the first time did a full calculation of what we call the anthropogenic, the human-induced greenhouse effect. So the science tells us and gives us a very clear picture about all that. Now let me make a remark on that, which is also very topical and very, very late and very new information. So a paper published, I think, 2 weeks ago. When we talk about El Niño and La Niña, so the ocean obviously plays a very important role in the planetary climate system. So as I said before, during El Niño, net heat is released from the oceans, and during La Niña, it's sucked up. Now, the last decade was more or less characterized by a lot of La Niña events. So it was, in a sense, or gave us the appearance of a slightly slowing down of global mean temperature. Now, if we do measurements of the radiation, the greenhouse effect, and the anthropogenic enhancement of the greenhouse effect simply means that sunlight is to some extent trapped by molecules, like CO2 molecules in the atmosphere, in the upper layers of the atmosphere. So it means, if you do an energy balance, if you just imagine you would have a sort of spherical umbrella around the planet, and you just look how much energy goes into the planet from outside and how much goes outside of its sphere. If you do satellite measurements and so on, you see that actually more energy goes into the system than out. This is the ultimate proof of human interference. But the energy has to go somewhere, of course. Now, it can be used to melt down sea ice, for example. That actually happens, but it's a tiny contribution. Most of the energy that's now the state-of-the-art hypothesis actually goes into the oceans. And once the oceans really suck up, swallow up, so to speak, a huge amount of energy, of heat, it will not warm up the surface, in particular the continents, the landmass. Now, in order to appreciate that, you have to imagine that the top 3-meter layer of the oceans contains as much heat as the entire atmosphere. So everything that happens within the oceans, and the ocean is up to 12,000 meters deep, really has a major impact on how much energy and heat is still there in order to heat up the continents and to heat up the atmosphere. So whatever happens in the oceans, if there is, for example, a transfer of surface heat into deeper layers, down to 700 meters or even lower, has a major impact on the surface temperature we measure. That seems to happen because this is a chart, very complicated, but it simply measures more or less the ocean heat uptake in the layer down to 700 meters. And you see, just before we had this seemingly slowing down of global warming at the surface, there was the highest on record swallowing, so to speak, of heat by the oceans. If you want to understand the full system, you have to measure what happens in the oceans in particular. So, of course, there is not a linear trend. The system digests the heat and the heat excess provided by the greenhouse effect. And it's very complicated and very difficult to predict what precisely happens in 1 year. But all these understandings and all this grasping of processes tells us that, yes, something dramatically happens. There is this excess energy, and it, of course, transpires through the system. The system tries to digest it, and it pops up in various places of the Earth, but also in various episodes in time. So the science tells us, because of this excess heat, we will see, in the end, a warming of the entire planet. And this is what the future will bring, actually, here. This is a very important chart, so you have to take some time for understanding it, and you have to keep on paying attention to this. Now, what you see on the left-hand side is a scenario for global emissions of greenhouse gases. So this is here in gigatons, that means billion tons of CO2 per year. This is the historical line. Actually, now the emissions have increased up to 35 billion tons of CO2 per annum, per year. And what will the future bring regarding emissions? In a so-called business as usual scenario, because we have a lot of coal and oil and gas in the ground, in a business as usual scenario, we would just go up with the emissions because other countries, China, India, Africa, would soak up the coal, so to speak. We would have a industrial revolution and industrial development like Europe had 2 centuries ago, and everybody would in the end become a carbonized society. If that happens for 9 billion people, when we would use most of the fossil fuels in the ground, and we would climb up to about 100 billion tons of CO2 per year for the global economic business machinery. When it would level off sometime, and maybe the decay would be a little bit different, this is highly stylized here, but nevertheless, there is not enough cheap fossil fuel in the ground to keep that level forever, of course. Now, what would be the outcome? This is global mean temperature developed since 1900 to 2010 here. And you would see this is warming above pre-industrial by 1 degree, 2 degrees, 3 degrees, and so on. Actually, according to this scenario, input into the atmosphere, we would probably have an increase of global mean temperature by 3 to 4 degrees by the end of the century. And if the world doesn't stop in 2100, which is not so likely, when this process would go on, it would mean that by the year 2300, that's the best guess scenario, so to speak. If you look across all the models we have, that's why you have this fan of colors here. If you just concentrate on the median here, then you find a warming of about 8 degrees. So that's the middle of the road prediction, actually, or projection. It's not the outlier projection. The middle of the road projection tells us that we would enter a stage where the planet would warm by about 8 degrees. And 8 degrees global mean temperature means that 10 to 12 degrees on the continents. This is just the annual mean temperature. It would mean that we might have heat waves which are 15 degrees warmer than what we have today. Now, if you add that in Northern Europe, for example, in Germany, I think the highest degrees we had in heat wave is about 40 degrees. Add another 10 or 15 degrees, that would be a completely different world. And there are many regions in the world which are already at the boundary of where a civilization can be sustained. So if you go to Libya or Saudi Arabia, in summertime you have 52 degrees. Add another 10 degrees or even 15 degrees, these regions would become inhabitable, actually. It would be beyond the physiological limit where humans can exist. So this clearly is something we should avoid. Now, it would be much nicer to have this temperature development, the blue fan. Again, you have the shades because you have included all uncertainties coming with the various models here. But what type of scenario for emissions do we need in order to stabilize here? It's the blue scenario, and the blue scenario means that we have to peak global emissions, including China, India, Latin America, Africa, by around 2020, then go down in global emissions to 0, actually by 2070, and then go to what we call negative emissions. That means you have to more or less suck up, extract CO2 from the atmosphere, about 3 to 4 billion tons every year. And only then in this scenario we get this fan of temperatures. That means we will scratch the 2 degrees line and then stabilize, and for many centuries to come we would still have an elevated temperature far above what we had in the Holocene. So that's the fundamental choice humanity has. That's why I call it Humankind at the Crossroads. And you can imagine what you see here, both scenarios are transformational. The red development means a complete transformation of our civilization as characterized by natural climate conditions. So how would a civilization of 9 billion people survive and sustain livelihoods and live in dignity under these conditions? Very hard to imagine. So we would have to reinvent our civilization, clearly. Or we would deliver this scenario, which also means we would have to decarbonize our societies rapidly. In a sense, it would be another industrial revolution. I come to that. So transformation is ahead of us anyway. Why 2 degrees? Well, this has to do with the nonlinearities. I have developed and introduced a concept together with a number of colleagues called the tipping elements in the Earth system. That is, if you think of the planetary machinery like a human body, you have sort of vital organs that would be destabilized, might even collapse, if you turn up the global temperature. It's like the body temperature, which you would turn up. So 2 degrees is already fever for the planet. 5 degrees would be lethal, actually. And so you would have disruptions of the summer monsoons in West Africa and India. You would have destabilization. Perhaps, it depends on many complicated processes of rainforests, in particular in the Amazon region. And of course, you would have a melting in the long term of ice sheets, like the Greenland ice sheet. Now we did pick a calculation of when will it happen, above what temperature threshold can we expect an irreversible melting of the Greenland ice sheet. And we found 1.6 degrees actually as the critical threshold. And when the Greenland ice sheet will start to melt, not entirely maybe, for that temperature, and over a long, long period of time, it can take thousands of years, but in the end, if everything is molten down, it would mean a sea level rise of 7 meters globally. But I should mention also that a very simple, but on the other hand, very important and dangerous phenomenon accompanying global warming and accompanying CO2 pileup in the atmosphere is ocean acidification. It's simply if you take water and add CO2, you get carbon acid, so to speak, or carbonic acid. And this means the water becomes acidic. And this is precisely what we measure now because of the enrichment of atmospheric CO2. But we measure already that the seawater becoming more acidic. And that has major implications, in particular for coral reefs. So we did also a calculation, what will happen to the coral reefs in the world. And we found that the combination of higher sea level, of warming of the ocean water and becoming more acidic, we find that above 1.5 degrees global warming, which is actually coming with this acidification process, we will lose about 90% of the coral reefs under current conditions. So it may be that the corals react and adapt in a miraculous way, but if we assume the current trends and the current behavior and the current resilience of coral reefs, we jeopardize, or the system is jeopardized and will risk to lose a huge part of the coral reefs. And this will actually happen not in thousands of years, this could happen over the next decades. And a world without corals would be a very different way, not just for tourists. So we have actually summarized many of the things we can expect in a 4 degrees world in a major report for the World Bank, which was released in November last year. It's called 4 degrees, turn down the heat, why a 4 degrees world has to be avoided. And this shows, and that's an element I want to introduce next, is it shows that global warming and climate change is an issue of equity. It has to do with fairness. And what you see here is if the sea level rises, when it will not do so in a homogeneous way. It will not be the same type of rise all over the planet. And this has to do with very fundamental physics. So, if the two big ice sheets start to melt, Greenland, for example, 2,000 meters of ice packed into a huge layer, if that ice is going to melt, when it will sort of go into the sea, flow into the sea. But if the ice sheet, the Greenland ice sheet, loses mass by this melting, it loses also gravitational pull, because the gravitational force a mass is exerting is actually proportional to that mass. So the water that comes from the melting of Greenland will be released by Greenland and will be actually flowing towards the equator. So that means everywhere on this chart where you have a red color or a dark red color, there is a disproportional increase of sea level, while around the melting ice sheets there is a disproportional actually reduction of sea level. And this is an amazing effect. And the same is true also for the heat waves, actually in a warmer world. Again, in relationship to the natural variability we have now, it is the tropics and the subtropics which would have the wildest fluctuations. Why? Because in the tropics, for example, the climate is very stable. During the day, during the night, during summer or winter, if there is anything like a summer or a winter, you have more or less the same temperature. So in the Congo Basin, you have 28 to 32 degrees all year round. If you add now 10 degrees for local positions or 4 degrees globally, actually, you see that in the tropics, things that under current climate conditions, heat waves happen just once in a million years, will happen every second year. This is not the same as in the sort of mean latitudes where Europe lies or North America or in the Arctic. So again, the tropics and the subtropics, that is the developing world, are hit disproportionately hard by global warming. So we have this very paradoxical situation that those countries who least contribute to global warming because they release very little greenhouse gases will be hit hardest. This is not just folklore, a sort of humanitarian folklore. It's unfortunately the physical reality here. So we have a big, big problem here. And now if we talk about equity, when we naturally refer to international organizations, first and foremost the United Nations, which are supposed to deliver something like international fairness. And the United Nations have a framework convention on climate change, and based on this framework convention and equity, they have sort of decided that global mean temperature rise should be confined to less than 2 degrees. There are many good reasons to confine it below 2 degrees. The question is, are the United Nations able to deliver on that? What I think is that the United Nations, yes, they have to tell the big narrative of climate equity, so we have to sort of draw the 2 degrees. We provide a framework and provide the contours of this 2 degree story. Now, how could it be achieved? This is a top-down approach. 194 nations are actually now party of the Climate Convention, and we all have to find a consensus on how to go forward. How could 2 degrees really be delivered? Now, here we are touching upon the very core of equity and fairness within the human discourse. Now, we could imagine that each person on this planet has the same right to use the atmosphere. So wherever you live, however rich you are, you have the same right to use the atmosphere, which means equal per capita emission rights. I'll come to that a little bit later again. Let me first of all say that we have this dilemma. If you have a global problem, and individual people in the end have to contribute to the solution, and most people say, what can I do? I'm just a drop in the ocean. No? There are 9 billion people in 2050. If I change my behavior, if I do not buy a big car, what difference does it make if all the others do not behave properly? And this is the eternal dilemma between the global good and the global conscience and the global responsibility and individual behavior. Now, there has been a famous philosopher who has solved this problem, actually, this dilemma. His name is Immanuel Kant. Through the categorical imperative. So let me refer to Immanuel Kant. Here he is. So he lived in the 18th century. And in the end he said, yes, of course, an individual person cannot deliver a global law, for example. What you contribute to the global good may not be sufficient, because all the others may ignore the good things, but without your contribution, it won't work either. So what anybody can do is to make the necessary contribution, because in the end, only if all the individual contributions sum up, if everybody contributes, you can solve the global problem. So it's not the sufficient contribution, but the necessary condition, the necessary contribution that counts. And this is actually enshrined in the so-called categorical imperative. Now, we have tried actually to operationalize Kant's approach because we tried, that is the German Advisory Council on Global Change, we devised an approach, a concrete approach, how we could solve the global climate problem in a fair way. This is the so-called budget approach, and it's based on two insights. One insight is that global mean temperature actually scales, is a linear function, more or less, of the cumulative emissions. So you just add up over the next, say, 50 years, how much carbon has been released, CO2, into the atmosphere. So you just add it up. And the total amount really brings about the change in global mean temperature in 50 or 100 years from now. So it doesn't matter so much whether in individual years you have less or more. It's the sum of the contribution that really counts. And we can calculate what we have in order to stay with a reasonable probability below the 2 degrees. We have, over the next 40 years, another 750 billion tons of CO2 to release into the atmosphere for the world as a whole, actually. Now, we can now work with different scenarios. We can imagine we would have a peak in global emissions in 2011. That has unfortunately not happened, because we are now in the year 2013. And then along the green line, we would sort of go down in global emissions. And the area under the curve would be the 750 gigatons, the cumulative emissions. Now, since 2011 has been passed already, we could imagine we have a peak in global emissions in the year 2015, that would be the blue line. Unfortunately, since we have more area here, the blue over the green one, we have to chip it off later on. So we have to dive down here with the global emissions. And if we wait until the year 2020, which is much more likely if it happens at all, so you would have this type of curve, you would have to phase out global emissions by the year 2040 completely. Now, if we assume we have a given budget, the area under either of these curves, how would we distribute it across the human population? And as I said, the Kantian principle would be each person has the same right to pollute the atmosphere. If we calculate this, means that we have about 2 to 3 tons of carbon dioxide to be released by every person on this planet every year. This means that you can drive a Mercedes 20,000 kilometers, and when your budget has been completely spent, or you can fly twice to New York City between Berlin and New York City. So it's not a lot, actually. Now, if you would do that, you could simply ask yourself, various countries, equal per capita emission rights. Now, the United States currently emit per capita, per person, annually about 20 tons of CO2. If we would just use till the year 2050 their budget, which is the same per capita as in every other country, there would be carbon bankrupt, if you like, by the year 2020. Other countries like Germany would sort of have their bankruptcy a little bit later, while a country like India, for example, in green, could still increase. So if you do that, you see that the three major country groups, so the industrialized world, the emerging economies like China, and the developing world, they have very different trajectories. Now, it is impossible for industrialized countries to phase out completely their carbon emissions by the year 2025. Well, of course, it would be very comfortable for the developing world to just increase their emissions and to peak in the year 2040. In order to come to a solution here, you would have to introduce emissions trading. That means some countries actually could extend their lifeline of emissions much further, so the industrialized country would buy carbon credits from those countries here, the developing countries, who would more slowly increase their emissions and actually peak at a much lower level. And this means that about 100 billion euro would have to be transferred from north to the south. So that would be the emissions trading system. Now, here is the other approach. If you wouldn't have a top-down approach, you would just say you deliver from the bottom by business, by specific states, by individuals, and so on, to 2 degrees, simply by changing behavior, by inventing smart business cases, and so on. So that's the alternative, and we have discussed this in a major report, the flagship report for the German Advisory Council in 2011, and it was called World in Transition, a Social Contract for Sustainability. It's all about the bottom-up approach. Okay, this is freely available. Please refer to the website of the WDGU. You can read the full report. So let me conclude by saying it's the two sides of the coin. The top-down approach is provided by the United Nations, a major narrative, a framework for climate justice in the end. But also this bottom-up approach where NGOs, business people, individuals actually just try to avoid the emission of greenhouse gases, often by behavioral change. And the two things have to come together. Now, why are we all doing that? Because what you see here, children's hands, the current generations, like the generation I represent, can still have a good living, actually, by burning fossil fuels, because the major impacts will only be felt in 30, 40 or 50 years from now. But everybody who either has children or plans to have children once in their lifetimes should consider whether they really want to push their descendants onto an inhabitable planet. Because it doesn't make sense on the one hand that you save a lot of money in order to provide a good education, maybe at Harvard, maybe in Cambridge, for your children, but to deprive them of the sustainable ecosystems they need and the nature they just love to witness. So maybe I should conclude with a joke or a quotation by Marx, but I don't mean Karl Marx, but Groucho Marx, a famous comedian. And he once said, "Why should I care for future generations? What have they ever done for me?" course we haven't done anything. So you see we have an asymmetry in time. We are actually influencing the fate of future generations. We are not influencing our fate. That means we have a responsibility. Because of that responsibility, we have to stabilize the climate. So thanks for listening.
So let's review the key takeaways. One, there is a substantial risk that we are disturbing the stable, enabling climate we have had for the last 10,000 years. Two, that change, that possible risk has everything to do with the carbon dioxide emissions that we are making. And if we insist on burning all the hydrocarbons in the world, all the oil, all the coal, all the natural gas, this is going to mean that we will increase the mean global temperature by 8 degrees centigrade, which is a complete transformation of our world as we know it. Three, any solution to this dramatic problem has to be based on equal rights of everyone to emit. Professor Schnellnhuber evokes Kant and the categorical imperative in substantiating this bold claim, and I think this is very significant, and we will return in week 8 to Kant, to categorical imperative and the golden rule. For this week you have a reading, a writing and a research assignment. Your reading assignments include the synthesis part of the IPCC's 5th assessment report, which just came out. It also includes chapter 6 of the World Energy Outlook from 2011. Your research assignment includes the climate indicator tools by the World Resources Institute. That tool is going to enable you to measure historical emissions, therefore historical responsibilities of key actors in the world. And I think that's an important benchmark to have. Your writing assignment, the question for your writing assignment for the week is about the causes and the consequences of climate change and what your proposal to solve this problem would look like. You have 500 to 1,000 words to make your case. Good luck.